Today we've got Shreyas and Vihari talking about predicting generalization of deep models.
Okay, right. So today we are going to talk about generalization of deep models, deep learning. So as you all probably already know, the classic learning theory does not explain very well why deep learning models generalize as well as they do. Right. In a nutshell, what classical learning theory tells us is that the difference between the test and the trial error, which is called the generalization gap, is upper bounded by this term on the right. I'm going to take it. Yeah, no. Okay. So this term on the right, and the term on the right has this complexity measure C, which is a function of a trained model and the training data, and M, the training data size. And then this would usually also contain some other tiny term, which is an artifact of the proof, usually. And so this holds with a high probability, according to the learning theory. And C usually is a measure that depends on the number of parameters of your model. And so this would predict that if you increase the number of parameters, such as you increase the depth of the model, then you should expect worse and worse generalization. But we know that that's not really the case. So the classical learning theory cannot explain deep models why they generalize. And so our objective here is to bridge this gap between what we observe in practice and what the theory can explain. So there's this big push towards trying to at least come up with empirical motivations for what a good complexity measure should look like. And what that means, if I rephrase, is we are trying to replace the C in our previous inequality with some empirical predictor, which is a function of the trained data and the trained model. And now if we have a good empirical predictor, that of course is going to motivate further theory. And of course, we will be, that can help us, give us more confidence when we are deploying models in practice. So before we go further, we should perhaps spend some time understanding what we mean by test error. Conventionally, the test error is the evaluation on some held out labeled data, which is called identical, which is identically distributed as a trained data. But this is also called the in-distribution evaluation. But as we will see with some examples later on, that in-distribution evaluation often overestimates the performance in the real world. The real world performance is far worse than what in-distribution evaluation tells us. And so people talk about out of distribution evaluation. We will define what we mean by that later on. So here we are attempting to go beyond in-distribution evaluation. And the hope is that out of distribution evaluation is a better proxy for the real world performance. And so therefore we'll be measuring the true progress in terms of model development. But we need to be a little careful as to what we mean by out of distribution evaluation. Not every definition of out of distribution may be a useful one. We will spend some time trying to define what we mean by out of distribution evaluation later on. Right, so this session is divided broadly into three parts. In the first part, we will be spending time with some existing methods that are proposed to explain in-distribution generalization gap. In the second part, we'll be looking at complexity measures that are proposed to explain the out-of-distribution generalization gap. And in the third part, we'll be relaxing the problem a little, and we'll be, instead of trying to come up with a measure that is correlated with out-of-distribution or in-distribution accuracy, we'll try and predict exactly the accuracy for any data set using only the unlabeled data. And then we will conclude with future work. Any questions? Okay. All right, so as I explained, in this part, we'll be looking at the one in the gray. It doesn't look as gray as my laptop. The accuracy predictor, which is a function of the fitted model and the training data. And then we are trying to explain the ideal generalization gap. This is the in-distribution generalization gap. We'll begin with this survey paper from published in Unclear 2020. And here, this paper does a good job of summarizing all the measures and then bringing them all under one umbrella and evaluating them on image classification datasets, CPAT and SVHN, although they only use ConvNet architectures. So the setup in this paper goes as follows. They generate multiple models by setting some of the common hyperparameters to a different value. These common hyperparameters could be batch size, dropout, learning rate, etc. And each of these 7 common hyperparameters take 3 values. And so there are 3 power 7, 2, 1, 8, 7 total models. And they denote by theta I the value assigned to the ith hyperparameter. And theta is denotes the value assignment to all the hyperparameters that they are looking at, the 7 ones, the 7 hyperparameters. And they denote by mu the complexity measure that they are trying to evaluate. And that, of course, is a function of the theta here, which with some abuse of notation is actually a function of the training model. And g theta here denotes the true generalization gap. And the true generalization gap is computed by evaluating on a held log test bed. And now we have mu and g, and both mu and g can, given certain number of models like theta 1 all the way to theta n, they both can give you some ranked ordering of the models. And now a goodness of the measure is, and ideally a good measure should align very well with the ranking that is given by g. Right? So the metric is that the measure should align very well the ranking with what G assigns the ranking to be. But in this paper, they argue that instead of looking at the overall ranking of the models, we should instead be looking at the models that only differ on one hyperparameter. So they propose this something called granulated Kendall's coefficient psi, and the psi itself is an aggregate over psi I, where I is the hyperparameter index. And so here what they're doing is, you can forget about the summation for the moment. And this is a ranking distance. And then they are looking at thetas, which only differ on the ith hyperparameter, while every other hyperparameter is set to some other static value. And then they sum over all the possible configurations, all the possible values for all the other hyperparameters. And so you can interpret this psi I to be, I mean, if mu has a very good psi I, you can interpret that to mean that the measure is very good at predicting the effect of the ith hyperparameter on the generalization gap, right? And so the overall psi value is just an average over all the individual hyperparameters, psi i's. So to understand better as to what I'm trying to say here, the psi I is a little tricky. So let's say we have 2 hyperparameters, dropout and learning rate, and each of the hyperparameters take, let's say, 2 values, 0.3, 0.7 for dropout, and learning rate 0.1 and 0.05. And so there are 2 hyperparameters and 2 values they can take. So we have 4 total models. And in order to, let's say we want to estimate psi 2, then we would look at the first 2 models and the second 2 models. The first 2 models, as you can see, only differ on the learning rate, and the dropout is the same. And the same thing for also the last 2 models. So we would look at the ranking assigned by mu and g, and we compare them, and then assign some scalar score for the first 2 models and the last 2 models as well. And then we aggregate that to get the final score for the second hyperparameter. So that's how the learning rate score is estimated, the cycle.
So it's sort of like marginal averages.
No, it's not. So
It's the same as marginal averages, where you have a uniform distribution.
Yeah. All right, I think now we can already jump into results. This table here, let me explain what all you're looking at. So the 7 hyperparameters that they considered are these, from batch size to weight decay, width. And we can ignore this part for now. This is just the overall ranking comparison, which we thought, which we agreed that this is not a good measure to look at. C, I have already defined, and each column shows here the psi value for the corresponding hyperparameter. And they also show here in the rows is the oracle 0.02 and 0.05, which means that the mu is set to G with some noise. So this is the comparison with this ensures that we are not fooled too much by the randomness. And ideally, Oracle 0.02, if you look at that psi value of 0.487, means that the best we expect in the best complexity measure would come as close as 0.487 and not to 1. Right? So that's why we had these. And now, if you look at the other rows, so VC dimension, number of parameters, all, and the inverse of the margin, entropy, and cross entropy are all some complexity measures that you are looking at here. And as you can see here, our starting observation is that VC dimension and the number of parameters cannot explain deep learning generalization. So that's what is also reflected here. So what VC dimension number of parameters are arguing is that as you increase the number of parameters, as you increase the depth, you should get worse generalization. But that's not really the case. So that's why we see the negative values. And overall as well, we see much poorer performance for VC dimension number of parameters. And in fact, they do much worse than some other trivial ones, like inverse of the margin or entropy or cross entropy, which have some at least positive values. Right? So these are starting observation anyway. Oh, by the way, so computing the VC dimension for networks is not trivial, and they are using some paper which was proposed in Neshaber paper 2019, which you can find in the speaker notes, the slides that I've shared. Right. So, and they also propose some norm-based measures, which have some good theory behind, but they didn't work very well on this. So in the interest of time, I'm skipping that. And I'm only focusing on the measures that actually did something useful. So the flatness-based measures are one such. So in order to understand these flatness-based measures, we need to do a quick recap of the Pack-Bayesian literature. So let's say we have this prior distribution over the weight parameters W, and we denote that by P. And after having observed the training data, let's say the distribution over parameters is Q, right? So then the expected generalization gap between the test and the train error is bounded by a term like this, which depends on the distance, the distributional divergence between the posterior and the prior, and also depends on some other term, which depends on the probability with which we want this inequality to hold. Right. So this comes from this McAllister 1999 paper, and in Neshaber 2017, they made the very simplistic assumption of setting the P and the Q values to be very simple Gaussian, and they also assumed a diagonal covariance, and also assumed that the P and Q do not change much. Even after seeing the data, the covariance does not change. And once you plug in these values, the term in the numerator comes out to be very simple. We get something like this. But in order to, also the same paper, in order to get some non-vacuous upper bound, they set sigma to be the largest value that you can set it to, such that the training error does not blow up. So you can look at U as the perturbations that you are adding to the W, and you're just setting sigma to the largest value such that the perturbations do not blow up the training error. Right? Any questions? All right. So instead of looking at the expected training error, we could also do the same bound using the worst training error possible. And so instead of the expectation in the training error, like in the earlier case, they have this inequality contains the maximum training error. And here instead of drawing U's from some distribution, they have bounded each of the U's, the perturbations, to be less than certain scalar value. And because the sigma in the previous slide, which is the distribution of the noise and the magnitude of the noise are correlated with this inequality, we can replace all the instances of sigma by alpha. And so we would get a new numerator term, which would look like this. Right. So, I mean, if you don't follow the math, that's all right. I think all I want to emphasize is that we have this measure, which is based on some norm of the term and some sigma term, and where the sigma is said to be this. And as you can imagine, if the W found is such that it is very flat in the loss landscape, then you would have a very high value for sigma, and so you would have the corresponding value, corresponding effect on the mu pack based measure as well. And similarly here, with respect to this worst prime error loss term, we now have, instead of sigma, we have alpha, and omega is the number of parameters that we have. All right, so now we have the two new measures, and also we could define some other measures based on 1 by sigma and 1 by alpha as well. And so the comparison would look like this. We have looked at these two measures, and also 1 by alpha and 1 by sigma. Alpha and sigma prime are different from alpha. I'm skipping the details here. They're slightly different. And this is surprisingly doing much better than any other measures. In fact, this looks like the best that you can get. And Oracle 0.02 is 0.487, and this is very much comparable. So on the datasets that they are dealing with, this is the best. 1 by alpha seems to be the best possible measure for taking it. All right. So, and then this survey concludes on this positive note that sharpness-based measures seems to be doing very well, at least on the datasets that they are dealing with. And after this clear paper, there was this Murex 2020 competition that was launched, I think by some shared set of authors. And then they have created an even larger benchmark with a lot more data sets and a lot more architecture variations than this paper. And then that led to many other people working on that, using that benchmark to publish more papers. And so this paper from unclear 2022 proposes a different measure, which is surprisingly simple, but again, surprisingly effective. Their algorithm can be described in like few minutes. As we have said, they're trying to compute the measure here. And this as an input is taking the target classifier F and the training data as trained, and also a GAN training algorithm A. And now using the training data set and the GAN training algorithm, they train a conditional GAN, and then they get this G and D, which are the generator and the discriminator networks. And now that they have the G and D, they generate a synthetic data set, and they do take some care to ensure that they don't change the label distribution of the original training data. And also the number of training points is the same as the number of, the number of synthetic points is the same as the number of training points. And now they just use the synthetic data to evaluate the test error on the synthetic data, and then that gives them the generalization gap. That's all. And yeah, so this they compare with 3 winning teams of the competition from Murex 2020. These are the first 3 teams. And the competition had 8 tasks, and they compare with 6 of them. They skip evaluation on 2 of the tasks because they say that it's challenging to train a GAN on those 2 tasks, either because of the skew in the label distribution or because just that the training data is not that big. And what's surprising here is, again, I think that this evaluation is slightly different from, this is mutual information that earlier we were looking at psi value, Kendall's coefficient and all, but I think that's a little irrelevant anyway. So the maximum possible value here is 100, and the higher the better. And then all of the 6 tasks that they considered, they're consistently good. Since at least reasonably good. And then they try to explain why GANs are so effective by claiming that the representational distance between the trained and the test points, the synthetic points in the representation space are closer to the test distribution than to the trained distribution and so on. But I did not find that argument so convincing though, so I'm skipping that. Right, so it's anyway, I think even the authors agree that why GANs are so effective is still a mystery, and that still needs to be followed by. And so I think that brings us to the conclusion of the part 1. So we looked at some empirically derived measures, and looks like we have good success in trying to come up with empirical measures that explain ID generalization gap. And it definitely looks like there's scope for doing even better, because as you can see here, the best value is far from the ideal one, 100. 100 is the best possible value that you can get there. And also the fact that there seems to be these simple measures that seems to be explaining its ID generalization gap and beating the previously proposed methods seem to suggest that perhaps we can do even better. And so a big limitation is, of course, of the previous work, we do not understand why GANs are so effective, and also it's not yet viewed into a learning theory the role of GANs in bounding the test level. Yeah.
Sorry, so if I understand correctly, in the last paper, what they did is they generated synthetic data using GANs and used that to predict the generalization now. So I guess my question is, what is the guiding principle for selecting that synthetic data? Like, how do you say the data that you have generated is actually effective? How do they select the learning algorithm using the GANs? Because that seems like a massive challenge.
Right, maybe it is, but they didn't find any sensitivity to the learning algorithm, GAN learning algorithm. I mean, empirically, they didn't find any sensitivity. In the sense that they found from Studio GAN library, they just downloaded the best ones there. I think it's a big GAN plus the debug, some such augmentation. And then they evaluated, they even mentioned that they didn't even change hyperparameters of this algorithm and just ran on these tasks and found it to be doing surprisingly well.
So it seems to kind of Boston correctly.
Yes. I mean, even the reviewers, when I was reading to this open review reviewers, the reviewers were like, this seems like way too good to be true. Yeah, it's surprising. All right, so I think this in the second part, as we have earlier mentioned, we will be looking at OOD measures that predict OOD generalization well. So far, we have looked at measures that can predict in-distribution generalization well. But in-distribution error, as I said earlier, overestimates real-world performance. To drive home that point more, consider this example. So here, this paper was trying to train machine learning model that predicts from a chest X-ray scan if the patient has pulmonary abnormality of any kind. All right, and as is often the case, although they were training on the training data set which is coming from multiple hospitals and multiple wards, as is often the case, they found that this machine learning model, although is doing very well on the hospitals that it has already seen, was not generalizing well to other hospitals. And then they went back to the blackboard trying to understand what really went wrong. And then when looking at the saliency maps, they found something like this, as shown in these plots. It was never really looking at the lung. It was just focusing on the metal token that is often placed on the left side of the patient to distinguish left side from the right side of the scan, right? And so you can imagine, I mean, different hospitals and the different, depending on the person who is taking the scan, would place the metal token slightly differently. You can imagine the same hospital might have an emergency ward and a non-emergency ward. And so if you can distinguish what is an emergency ward, it has a very good likelihood for the patient being abnormal of some kind, right? So what I want to say is, if you are only looking at the in-distribution error, in that you are only evaluating on in-distribution, then such kind of errors will go unnoticed. So that's why you may have to look at new hospitals, evaluation of the new hospitals that are not seen during the runtime, which is what we are calling as out of distribution evaluation. The same thing also happened with these guys when they were trying to train models for COVID-19 detection. They found that the machine learning model was only looking at diaphragm region and the heart region and some other peripheral features such as the distance from the lung to the border or some such, which are irrelevant to COVID-19. Of course, here again, they found that the model was doing very well on ID in distribution, but of course, the model was not generalizing well to other distributions in the sense other hospitals. All right, so to drive it home even further, I just want to say that in identically distributed assumption that the learning theory often makes is a big myth, and that's violated very often in practice. So this paper from ICML 2019, for instance, was trying to consider a very interesting question. Does ImageNet classify as generalized to ImageNet, in the sense that they're trying to synthesize a new ImageNet test set, and they are very sincere in following the same data generation process as the original ImageNet ASCII10 data set. And despite all their efforts in trying to replicate it, they found that the new test set, previously trained models on the original ASCII10 training data had a reduction in performance by 3 to 15% on ASCII10 and 11 to 14% on ImageNet. So this, they have carefully considered why this drop in performance is, and then they attributed it to distribution shift. The sense that they said the new test set that we have synthesized has more harder examples somehow. So I think the summary of this paper for me is that it's hard to replicate IID, identical distribution, even if you try, right? And now when you deploy models in the wild, of course, no one's trying to be IID in any way. And of course, you would have distribution shifts. So yeah, as I earlier said, we need to carefully define what we mean by OOD. Consider this. Let's say there's this natural distribution of inputs. Let's say there's this encompassing space of every possible scan that you can make, every patient demographic, every scanner, and so on. And that is your big ball of natural distribution of inputs. And training distributions often only look at a sparse sampling from this natural distribution of inputs. And OOD evaluation, out of distribution evaluation, is about evaluation on distributions not seen during train time, such as the yellow ones here. So we will see an example. For example, as I was saying, in the medical diagnosis application, in distribution would be evaluating on the hospitals that you have already trained on, and out of distribution evaluation would be evaluating on any hospital. And similarly, you can think of a speech recognition application to be when evaluated on the speakers that you have already trained. That is your in distribution, and OOD would be any speaker, any speaker, any device, any noise environment, and so on. Right. So in this part, we'll be now shifting gears a little, and we'll be looking at. If you remember, this is a slight departure from our earlier slide of the same kind. We'll be now looking at accuracy predictors that explain the real world or OOD accuracy. And also we relax this. Earlier, this was just training data, and now we relax this to be access to training distribution. And now Shreyas will continue from here.
All right, awesome. So yeah, to reiterate what Vihari said basically is, when you talk about generalization from a very theoretical perspective, it's easy to make this IID assumption. It's easy to write down what IIDness is. You always assume your train and test distributions are IID, and you can make a lot of strong theoretical claims. Technically, you could do this for the OOD setting as well. If you could sit down and enumerate every possible shifted distribution or OOD distribution that you could encounter, and from like a packed Bayesian perspective, you could end up with some sort of generalization bound. But in practice, this doesn't happen. And if you do want to deploy these large-scale models in the real world, you kind of need to step beyond a very theoretical framework, because like the bounds you end up with are vacuous in a lot of cases, and it's hard to just categorize all of these things very succinctly. And so over the last few years, there have been 2 or 3 papers that have done a very large-scale empirical study of these complexity measures that could correlate well with OOD performance. And now OOD performance here could also mean, it specifically means the data sets that they picked in these large-scale studies. And their hope is that if they pick enough of a variety of data sets and distribution shifts and OD nest, then the complexity measures that they measure, like generalize to the real world. And there have been a lot of like fancy measures that have been suggested to tackle this problem, but I think like some of the simplest ideas out there are that as a machine learning community, you're basically always trying to optimize for in distribution performance. That's sort of, like it might be a broken goal. It might be not the best thing we could do, but a lot of benchmarks are set up to that. A lot of like state-of-the-art models claim good performance on this. And what this paper in Nearest 2020 found is that in distribution performance itself is a surprisingly strongly correlated metric for out of distribution performance. And more surprising than that, not only is it strongly correlated, but there's this very fascinating, almost linear trend between in distribution test accuracy for a model and its out of distribution performance. And so, they do this large scale study over a whole bunch of image classification data sets and ConvNet and ResNet models. And what they find is that you basically evaluate your models on in distribution, you get some sort of accuracy, and then considering a vast variety of OD data sets, which include OD data sets that follow the same distribution, like CFAR 10.2, which has the same distribution as the in distribution CFAR data set, or ImageNet v2, or you could consider corrupted versions of these data sets, such as the CFAR 10 corrupted splits, or you could consider something like the WILDS data set, which consists of a bunch of images of wildlife and animals from real life cameras, where the OD split consists of cameras that have completely different viewpoints from the in-domain training distribution. And regardless of what they considered and what they threw at this problem, they found, like a very strong linear fit, which it's a very surprising result, because classic generalization theory would tell you that the accuracy of your classifier on the training domain minus the accuracy of your classifier on some out of distribution domain is just upper bounded by some divergence, or like distance measure between these two distributions. And so that would sort of give you a band around this x equals y line on these plots where your points for different models will lie. But instead of that, they see a very strong linear behavior. And this linear dependence, they found, works really well, even if you change your model hyperparameters like width, batch size, learning rate, all of those things, it still translates really well. And you could train your model for long periods of time or for shorter periods of time, and you still get this behavior, which again is surprising, because the common belief is that the longer you're training your model on this in distribution data set, you tend to have some sort of overfitting behavior, where the longer you train, the idea is that the model is now tuned to more spurious features in the test distribution that is helping it make higher accuracy predictions. But on this large scale, on these large vision data sets, they didn't see that behavior. In fact, the longer you train and the larger the model is, the better this correlation with OD performance. And yeah, so the higher the training data set size as well, the better this OD performance. And so this paper kind of basically says, like you can be worried about how your models are going to perform in the real world. But for this specific setup, if you're looking at vision tasks, if you're looking at ImageNet trained models and evaluating on a bunch of these data sets, you can continue doing what you're doing and continue sort of gaming the in distribution metric in some sense, because it does translate over pretty well to OD performance. Yeah.
Anyone who case where you train the model on the training itself, fine tune the kind of out of distribution itself. These correlation.
Yeah. So there's actually a slide that we skipped in the interest of time, but they show that models that are pre-trained and then do zero-shot classification actually have an even better linear trend to OD performance. But as you start fine-tuning your model on the test, on your in-distribution training data set, you tend to lose that. The slope tends to become a bit more negative. So in some sense, zero-shot classification is more robust than fine-tuning your model on the in-distribution data. And that kind of makes sense from a lot of the work on pre-training, that where the idea is that pre-training is just giving you more robust features across a larger corpus of images. And
it's your for fine tuning and probably
Yeah, but at the same time, if you train from scratch, they don't see overfitting behavior as well. So it's an interesting observation where if you're training from scratch, you don't really overfit the test distribution, but zero shot performance is still slightly better. So I guess there is some overfitting, but it doesn't show up on these linear trends, right? Yeah, and so what this paper suggested was you can look at in distribution accuracy, and that's like the only metric you need to worry about. But a few years later, there was this paper which came out very recently, actually, near 2022, where they do an even larger scale evaluation on even more data sets and models, and they consider a large set of metrics and measures that you can evaluate on your in-distribution data, and try to find what the exact IID, OD accuracy correlations might look like. And they found that it's obviously more interesting than this linear trend, but in some sense, the in-distribution accuracy is still the best. So to talk about what the setup was, they basically consider about 170 different in-distribution and out-of-distribution pairs of data sets. They only focus on models that were pre-trained on ImageNet, and then these models are taken and fine-tuned on the in-distribution data set that forms the first of the pair. And then the metrics that they consider are, regular classification error, log likelihood, the calibration error of the models, the classification error under adversarial noise. And they evaluate these metrics on the in-distribution test set, on a third held out OD test set, and then on corrupted versions of the in-distribution test set. So for people who've, looked at these before, corrupted data sets such as ImageNet-C and CFAT-NC have about 17 to 19 synthetic distortions of the image, like Gaussian noise, blurring, low pass, high pass filtering, and so on. And obviously, they have a whole strategy for picking hyperparameters on held out experiments. And what they find is that the linear trend is not as common as the paper in 2020 proposed. So you could have cases where you have sort of a super linear trend where as you increase in distribution accuracy, or OD accuracy goes up a lot more. You could have more of a vertical line where there's some sort of underspecification in the task, where you could have multiple in-distribution models that don't improve upon OD necessarily, or you could not get too many gains on OD by training your models to better and better accuracy. Or there's very weak correlations, but if you squint hard enough, you could maybe fit a line to that scatter plot. But the interesting thing that they did find is that you never see a negative trend across this very large scale system of experiments that they considered. You never see a negative trend with increasing in-distribution accuracy and worsening OD performance, which again is a very surprising result to some extent, because we do believe a lot that overfitting is a thing that happens in deep neural networks a lot. Yeah.
Why we worry about automation, the robustness and all. Maybe the typical examples that we observe in the real world are really the heavy tail behavior rather than auto distribution behavior. You observe or testify that's quite far in the tail, your model is not very good at, rather than distraction.
Yeah, I mean that's a good point, but I think the issue is that you could always sort of come up with points where you want to deploy a model where you're sure that it doesn't exist in the training data set. And you can always argue that there is some aspect of the real world that any amount of human engineering or adding to the training set or making sure you have heavy-tailed enough of a pre-training corpus might not cover, especially for more sensitive tasks where you can design it as well as you want, like in self-driving or whatever, but you still end up with cases where a truck's carrying a bunch of traffic lights and these Tesla models are going insane because they imagine a whole bunch of traffic lights showing up on the screen. So I think you still need to have some sort of notion of robustness, even if you can't decide what OD is exactly.
But besides that, I think every test set is considered to be out of distribution in a sense, in the sense that it's hard to have exactly the same distributed identically distributed test set. So every test set has some distribution shift in a way. For example, if you have a Siri that is trained on some American speakers, then of course Siri is deployed globally, and how well does it do on Indian speakers? Right? So there is always a lot of distribution, and the test set. Okay, so I think that's what I was trying to say, this in that there's no in-distribution test set as such, and you should always expect distribution shift when you deploy a model in the wild, and a robustness of a model to that distribution shift tells you, it gives you a proxy for how good your model works in the real world.